and Radboud University in the Netherlands, and it's my pleasure to be the chair for this opening session. The speakers have 30 minutes with then 10 minutes for a discussion after each talk, so I will try to give you a warning slightly before the end of the talk. So our first speaker is Gustavo Lozano from the University of Buenos Aires, and the title you can see already is there, Vortex-Vortex Interactions in Superconductors with Nematic Order. So I think over to you.
Okay, thank you. Well, thank you for the invitation to the local organizers. Also to Nathan that created this center. At that time, many years ago, we had Nathan visiting Buenos Aires where we were discussing to create a center like this. I'm happy that he managed because it's always better being a visitor than being the host. So it's very happy to be here in São Paulo for many years. Now it's my first visit after 20 years, so I'm very glad. Okay, so I'm going to talk about vortex interactions in superconductors with nematic order. I try to keep, because I think we come from many different backgrounds, so I try to keep the talk basic. But of course, I'm staying for 5 days, so anybody who would like to discuss more details or more technical stuff, I'm very happy to discuss during the breaks. Also, for the younger people, don't be afraid to ask whatever you like. I might be able to answer or not, it all depends. So my main field of research is originally field theory applications in condensed matter. I work in 2 different fields. One is out of equilibrium evolution of quantum systems. It's a subject more related to statistical physics. And the other field of research is more related to superconductivity. Is what I'm going to talk today. This is a long project that I started many years ago with an experimental group in my physics department, which is the physics department of the University of Buenos Aires. The experimental group in low temperature physics is which I'm collaborating with, is it working? This here. Victoria Beckeris and Gabriela Paschini. They are 2 experimental physicists. And this work I'm going to talk today is related to a PhD thesis research by student Ramiro Severino. And in this particular work, I'm going to talk today, participated Eduardo Franklin, that probably many of you know. He's a well-known physicist in condensed matter physics. He's in Illinois, in Urbana. And Pablo Minini, which is another theorist from my physics department. He comes from another completely different subject, which is fluid dynamics. And you will see how he participated in this project. So this is a project that involves experimentalists, people from fluid dynamics, and people from originally condensed matter physics. This is the work I'm going to talk about. This is, it's been on the archive for a couple of months. It's on referee under the Physical Review B. I hope it's going to be published soon. Okay, so let me give you, this is a general outline of the talk. I'm going to give a general introduction, what we are studying this problem. Then I'm going to try to give you some details of the model we are dealing with and the numerical method we are using, which is this, because that's part of our contribution. We are implementing a new numerical method in superconductivity. The method is known in other areas of physics, but not in, well, as far as we know, not very well known in superconductivity. And then I'm going to tell you what are the problems we are looking right now, which are very, well, for us, are very interesting problems. Okay, so the main focus of our research is related to the discovery of a new kind of superconductors. This is like more than 15 years ago, in 2006, are superconductors that are based on iron, which is a not very common or intuitive compound to be found in superconductors, because iron is a magnetic element, and magnetism and superconductivity don't go along very well. So it was a kind of surprise when these people in Japan discovered superconducting properties on this kind of compounds. And since then these kind of compounds were studied in details. From the theoretical community, the interest was, of course, unconventional superconductivity was known from the 80s with high DC superconductors, the cuprates. But as you know, there is not much of consensus about the microscopic theory of unconventional superconductors. And the discovery of these new unconventional superconductors was welcomed by theoreticians because they thought that they could provide a new playground where to try ideas to explain this kind of unconventional superconductivity. We call unconventional superconductivity superconductors that cannot be explained with the usual BCS microscopic theory, okay? So after this original work, many works and many other compounds were found. I'm not very good in chemistry, I have to recognize, but probably some of you are. So I just reproduce this figure. Okay, there are all these are superconductors, which the common element is iron, but they can combine with group 15 or group, well, the other one here should be like group 16. And these are families of these kind of superconductors that are called, well, this is the name, is iron-based superconductors, okay? These are the kind of structures that appear, and they are around, they've been around for more than 15 years. There are many groups that can fabricate these samples. It's not very easy to fabricate them. And they can be built in very small structures, okay, for the moment. So these are the typical materials used for these superconductors. As I told you, there is not a consensus about what is the microscopic theory explaining this superconductivity. You know, conventional superconductivity is based on the idea that phonon interactions provide the binding force for electrons to form a Cooper pair. Here, we don't know. I mean, at least I don't know, and the people that claim to know, they fight each other, so let's say we don't know. But more or less, what is more or less accepted is that nematicity, which I'm going to explain now, what it is in this context, plays some role in this mechanism. Again, there are many theoretical ideas around that, but the idea that nematicity is playing a role in the explanation of this behavior is more or less accepted in different versions, okay? The idea of nematicity originally was introduced by Eduardo Fradkin. That's why we're working with him, and many co-workers like Kivelson, these people that I mentioned here, in the context of cuprates, okay? But they found that many aspects of cuprates are also present in these iron-based superconductors, and there is experimental evidence, which I'm going to show you now, that shows that there is a kind of nematic behavior at least close to a superconducting transition. So the emphasis on this work is trying to elucidate which is the role of nematicity in the superconducting properties of this material. Okay, we are going to try to focus how nematicity manifests in some aspects of superconductivity. That's the general field where we are working on. This is here is some papers that show you the idea of how nematicity appears in this. Well, these are cuprates. Here is in iron-based superconductors. These are all experimental and also theoretical work on this enigmatic nematic phase, because it's kind of because the people talk, when they talk about nematics, sometimes they talk about different things, but they are all nematics. So there is not much agreement on what it means, but there are several groups, experiments, and theoreticians claiming that nematicity plays a fundamental role in this kind of unconventional superconductivity. So what is nematicity? Probably most of you know, nematicity appears in liquid phases. This is in classical physics. Nematicity is very well known. It's a very well understood problem. It happens when molecules, we have an elongated structure, they aggregate, breaking rotational invariance. Okay? So they aggregate all pointing, following the same direction. Okay? This is nematic order in liquids, which is, in principle, is in a free space. Molecules which are elongated, they, in some cases, they accommodate all in the same direction. They break rotational symmetry, but they don't break translational symmetry. And when that happens, one says we are in a nematic phase. Okay? This is very well known. It's in every textbook. And the nematic order parameter, in general, in this case, is a tensor. And the description of nematicity in liquids is a very well-known subject. Okay? It's in textbooks. Okay? If you go to textbook, there's a chapter on it. Here, in what we are discussing now, is a little bit different, because we are not talking about liquids, but we are talking about electrons in a solid. Okay? So the claim is here that there's something similar to nematicity of this type, but in electrons in a solid. Okay? It's very difficult to find someone who tells you exactly what it is microscopically, this nematicity. Like this picture that you have for liquids doesn't exist for what I'm going to tell you. But the claim is that something similar happens. Okay? There is asymmetry that is broken from, that has to be with rotation in space by the electronic system in a solid. Okay? This transition, this nematic transition in a solid is, in a solid there is a ion lattice, and this nematicity transition is very related to a structural transition in this kind of compounds that occurs when these compounds have a transition from a tetragonal structure to orthorhombic structure, okay? Which in a solid breaks a C4 symmetry, breaks rotations under 5/4 degrees, okay? So this symmetry that is broken, this rotational symmetry that is broken, is associated also with a nematicity. Now, the point that is behind this is that many of the properties that are observed in these superconductors cannot be linked to a simple transitional structural change of phase. what they mean, I will show you some examples, is that it's not enough to assume this structural transition to explain all the things that happen. Because this distortion of the lattice is very small to explain the huge difference that appears when one measures physical observables. So even if nematicity is linked to this structural transition, the claim is that this structural transition is not enough to explain all the physics. So there is something else that has to be with the electronic structure of the solid, okay? Not only this structural transition. So a phase diagram of this kind of compounds has this kind of structure, okay? There is, this is a temperature, this is doping, where you change one of the atoms in the compound, the percentage of this atom in the compound. What you see here is that at a very low temperature, this, for some compositions, these materials become superconductors. This line here represents the structural phase transition, okay? That is called with TS. This Tn, this N doesn't have anything with nematic. The N is related with nil. Oops. With nil. So this phase is magnetic, okay? But people believe that this area here between the structural and magnetic transition presents nematicity, okay? So this is the nematic area, okay? And this is this area has been studied very well by different experiments. I mean, close to the superconducting transition, but in the metallic phase. And this area is less understood. And this is the area we want to understand. I mean, nematicity and superconductivity at the same time, okay? The area that was studied very well experimentally is this area that is here. And I will going to tell you how. Sorry. So our collaboration with the experimental group started many years ago, but like, I can't remember now, 6 years ago. I collaborated in a project where the experimental group was studying exactly, they had a crystal of this compound, and exactly at this composition, okay? And they were studying, that's why it's marked this red line, because that compound that they had, because someone sent them the crystal. We studied some experimental details of that compound around this area, okay? I'm not going to tell you about this experimental paper because I'm going to focus now on these new results that we have now. But I would like to tell you that when I tell you that people study experimentally the systems, what they do is they measure resistivity. Okay, you have this material, and you are breaking you have material, and you are breaking rotations in this material. So you measure resistivity in this direction, and you measure resistivity in this direction. So, and this quantity, which is the difference in resistivity in one direction and in the orthogonal direction, is a measure of how broken is nematicity. If nematicity is not broken, that should be 0, because it's the same measure in this direction as measure in this direction. But if that is different, that means nematicity is broken, okay? So people usually, when they play with experiments here, they have a piece of material, and they play making compressions of the material or pulling the material, and they see how resistivity varies with the stress, which is more or less what this formula is telling. And of course, nematicity is related to stress, but they define this nematic susceptibility, and they find that this susceptibility has a divergence, like Curie law, okay? And this is the signature of a nematic phase transition, okay? The claim is that this differential resistivity is too long to be explained only by structural physics. It needs to be something else. And these are the many cases that have been studied, different materials, and all coincide in this physics. But this is the experimental work we did some years ago. But the point is that, let me come back to here, is that to measure resistivity, you need to have resistivity. That means you cannot be in the superconducting phase which there is no resistivity. So all these experiments have been made in this sector where the system is metallic. So the evidence of nematicity is well understood in the metallic phase of these materials. But this effect is less known in the superconducting phase. So what we want to know is how nematicity manifests in the superconducting phase, okay? Now, the approach we use is, as you know, when there is no, when you don't agree with the microscopic theory, you can always go to a phenomenological theory, and the idea is to use a Ginzburg-Landau theory approach to study the superconducting phase. In particular, we know that these superconductors are type 2 superconductors that are characterized by vortices, and we want to understand how vortices behave in this phase, to see if nematicity plays some role in the behavior of the vortices, or otherwise say, if looking at vortices, we can understand how nematicity manifests, okay? So the idea is to study a phenomenological theory of nematic superconductors. That's what we did. Have to speed up, no? Well, the superconducting, the Ginzburg-Landau theory, probably most of you, even the younger people, are very familiar with it. This is the superconducting, standard superconducting parameter. We assume it's S-wave, but could be otherwise. This is a magnetic field. This is a covariant derivative. And everybody knows that this is conventional superconductors are characterized by the Ginzburg-Landau parameter, where lambda is the London penetration length that has to be with the penetration of the magnetic field in the superconductor, and C is the superconductor coherence length. And the ratio of these two lengths, characteristic lengths, define how the superconductor works. If it is well known that if kappa, which is the Ginzburg-Landau parameter, is greater than 1 over the square root of 2, the superconductor is type 2. That means vortices exist, vortices networks exist. And if kappa is less than 1 over the square root of 2, vortices do not exist, and the superconductor is type 1. Okay? This was the work of Abrikosov in the 50s. When the microscopic theory of superconductivity wasn't known yet. But still, using the phenomenology, he could predict the existence of vortex lattices in superconductors. Okay? This was a great contribution of Abrikosov in the 50s. This difference between type 2 and type 2 and type 1 superconductors can be also understood in the sense of attraction or repulsion of vortices. One can show that for kappa less than this critical value, vortices attract, and the lattice of vortices exists only with kappa is greater than this value. Okay? This is very well known since the 50s for standard superconductors. Now we want to see how this changes when we add nematicity. Okay? For nematicity, we need to add a nematic order parameter, and in the case we are dealing with, the nematic order parameter is Ising-like, is a single scalar, and that the two values that can take in the correspond to the breaking of this rotational symmetry, and the way you can couple the standard superconducting parameter is this B quadratic term, okay, and which is quite standard, this term, and this term, which is less obvious, that respect the symmetry, because when x goes to y and y goes to x, eta changes to minus eta. So this energy is invariant under this symmetry, and when this eta is different from 0, the symmetry is broken. Okay? So this is the Ginzburg-Landau theory for the simplest Ginzburg-Landau theory for nematic order. Okay? So what we want to do now is to study the dynamics of vortices in this kind of superconductors. And for that, by the dynamics, we choose a dissipative dynamics, which is obviously given this form. And this, in the case of standard superconductors, was done in the 60s by Schmidt in the 60s, who proposed the time dynamics of superconductors with this dissipative dynamics. Okay, this was proposed already in the 60s for standard superconductors. Okay, so these are the equations that are well known from the 60s that, for a standard superconductor, explain the evolution of a superconductor. So this theory was these equations can be easily adapted when you have an additional nematic order parameter, which is like this, okay? And one would like to solve these equations. These equations typically are solved using this finite differences methods. This is the standard way to do it. Those methods are not very stable, to our opinion, and very difficult to implement and very time-consuming. And the idea here was to use an alternative method that is very well known in the area of turbulence. That's where these people from fluid dynamics come from. They use very efficient methods to solve equations from turbulence. And the equations from turbulence are very similar to Landau equation. So the idea was to see whether that method could be applied to superconductivity. And the answer is it can. I can give you later details about this numerical method. It's called a spectral method, meaning that it's not solved in space, but in Fourier space, okay? And has been developed from the 2011 by this group of fluid dynamics of my department. The program is called GHOST, because coming from geophysical high order suite for turbulence, and you can get all these programs free from this site. Okay. So what we did was to solve first to check the method with the known results of the standard superconductors. Here we plot density plots from the magnetic field for different values of kappa. This is one vortex only, okay? And you see the kappa is the ratio of two characteristic lengths, with kappa equal 1 over square root of 2, the magnetic field penetration length is the same that the superconducting coherence length. That's why if you look to the density profile of the vortex from the magnetic field and the superconducting parameter, you see the same size. But if you look here, kappa is greater than the critical value. You see that the magnetic field is fatter than the superconducting field here, and here is the opposite situation. We could get all the standard results for the standard problem. We study how am with time? 5 minutes? Okay. We studied how the biquadratic coupling affects the profiles. This is only to check the system. And then we studied how is the effect of this new coupling, which is, remember, is related to this coupling here. Well, here I changed the notation. Sorry, this is superconducting order parameter, and this is the nematic order parameter. And what you see is that you have elliptical vortices, and the orientation of those vortices depends on the sign of this parameter. So in the case of vortices, the nematicity can be seen by the elongation of vortices. But also, what we wanted to see is how these new couplings change the value of the critical kappa, to see whether these new couplings provide repulsion or additional attraction to vortices. Okay? So, well, I will skip this, but sorry. I will skip this part. But the idea then is what we did is we put two vortices, and we were looking whether they were attracting or repelling. Okay? And that can be done because we are solving the dynamical equations. And the critical value was determined in the moment that the vortices changed from attraction to repulsion. Okay? And this is very easy to do. Well, very easy after you write the program. You try it for 1 year, but it takes some time. But after that, we were putting vortices, and then we were determining whether they were attracting or repelling. Okay? And that's the way we were determining how kappa was changing. So here we put two vortices one over the other, and we let them evolve, and we see that they separate. That means that the attraction is repulsive. Okay? If we change kappa, it can be a situation where you put the vortices separate, and you see how they go to each other. So that's attraction. And then we were playing with that in different situations of parameters. Let me skip this, because these are details. And, sorry, these are details. I'm sorry. We were playing also with, in the case with nematic vortices, when they were attracting or repelling. That was different cases of attraction and repulsion. And what we could do was to determine how kappa critical was changing with the two typical values of this is lambda 2, which is the biquadratic coupling, and these are different values of the lambda 1 parameter, which is the truly nematic parameter. So what we see is that lambda 1 always lower kappa critical, meaning that they provide additional repulsion, and the biquadratic coupling provides an additional attraction. So the two terms place one against each other. Okay? So we could determine also the energy as a function of space numerically with the efficient method, and we could play also with different kind of more complicated configuration of vortices. This configuration with 4 vortices altogether originally, and they evolve, sorry, they evolve, they separate first in this way, then they evolve like this, and then they evolve in this way. We can, with this method, we can put as many vortices as we want. That's not difficult technically, and we can play with all the kind of vortices we want. So what we are looking now is that in this system, because of the characteristic of the nematic or the parameters, there can be also domain walls. A domain walls of the nematicity means that in some part of the material, the nematicity can take a value, and the other part of the material, the nematicity can take the opposite value. So there is a wall here, which is a domain wall, which everybody agrees that walls are at the same place than the structural twin boundaries of the material. We know that twin boundaries act as pinning for vortices, but the point is that we think that experimental people and also theoreticians, we are a little bit confused about the role of the twin boundaries and the domain walls. People try to confuse the role of two of them, and what we are trying to do now is to separate and trying to understand what is the difference between the standard pinning of vortices by twin boundaries, structural twin boundaries, and nematic twin boundaries, okay? Nematic domain walls. So now that we are working that at present, okay? And this is experimental work where you see the twin boundary. These lines, okay? These white lines are twin boundaries, and these blue points are vortices. And these people can take the vortices and move them in the material. It's very, I mean, experimentally it's great what they can do, and they can play with that. And here they take a vortex through the wall, and they see this deformation of the vortex that is very similar to what we are finding numerically. This is a numerical simulation. This is the experimental work. This deformation, I mean, in a standard superconductor, this would be, the vortex would be circular. Okay, here in the domain world, takes this form that is like this. This is the wall. Here the vortex wants to be like this, and in this side the vortex wants to be like this. So it's like an ovni. It seems that we are seeing the same numerically with this simple phenomenological model. Okay. Okay. Then I think this is what we try to do. I mean, I think part of the nice part is to have introduced this numerical method, which is very efficient. And, well, that's all. So thank you for your attention.
Okay, thank you very much. Are there questions? I'm sure there are some. Yes.
So, thanks, Nematic. So, you have mentioned how this appears in experiments in the barium 122 compound.
Yeah.
Also, iron 7I has a very clear nematic. Iron 7I has a very well-known nematic phase.
Yes.
And it's also superconducting. It's not working like this one. Are there any experiments in iron selenide, and how do they relate to your work?
Thank you for the question. Yes, there is a. In fact, it seems that the compounds based on barium and what we call Buffet-Coas are different, complete in the opposite way of compounds in iron selenium. And there are groups working with that. It's the group of Catherine Moller, and they have very nice experiments too. And in fact, it seems that in what case the vortices are attracted to the walls, and in the other case, this is iron selenium, and in the other case, vortices are repelled by the walls. Which, if you think of the wall as only structural, it's not very intuitive because walls tend to always act as spin centers. But from the point of view of nematic, it's only to change the sign of the coupling, which is completely arbitrary. So yes, we are comparing both experiments. And we think that the phenomenology is opposite, but easy to explain. Still, these are toy models, so the idea is to explain more or less the behavior.
So I have microphones. So a simple question about structure. So these iron-based superconductors, are they also considered as two-dimensional systems?
No, they are less two-dimensional than the cuprates. Mm-hmm. There is asymmetry in the third direction, but it's not so strong as in the cuprates.
And what about the planes, if there are some planes? Are there square lattice?
Well, there is a change of phase from tetragonal to orthorhombic according to the temperature.
The planes.
Yes.
Okay.
Yes.
Okay.
But they are not so anisotropic like ITC.
And the elongation of the vortices is along which direction? Perpendicular to the planes, or?
We are thinking that in this simple simulation is that the vortices are directed in the C plane, C direction, meaning orthogonal to the planes. Okay. But we could that we can relax. The simulation can be done without assuming that. This is simple, but it's not a limitation.
Thank you, Professor, for the talk. I think it was really interesting. My question is that I just got curious about the method that you used to solve the partial differential equations. I wonder if you could give us just like the main idea, or how different is it from the finite difference method? Thank you.
Yeah, yes. The main idea is that instead of finite difference, you make a mesh on your material, and you discretize the equations in space and in time. And you have to do a lot of things because it's not as simple as it looks. But the problem with this is that it's very time consuming. If you want to put a smaller mesh, it takes a lot of time to solve it. This method is a group of methods that are called spectral methods, meaning that you transform to Fourier. Of course, these are nonlinear equations, so it's not as simple when you want to do it. The secret of these people is that they manage to deal with the nonlinearities in Fourier space. And they have a lot of recipes of how to go and back from real to Fourier space. And this is very efficient numerically. It can be implemented in normal computers. You don't need a supercomputer to solve. You can run in a laptop, okay? And they can study even more complicated problems like this, that is quantum turbulence, which is much more complicated than superconductivity. So the methods are really great. I didn't invent the method. I'm just selling it.
Hi, thanks for that talk. It was very nice. I was just wondering if you can control the transition temperature of this nematic phase with the distance between the iron and selenium, for instance.
Sorry?
The distance between iron and selenide and the selenium atom. The Chalcogen height.
You are asking about the critical temperature of this? Yes. The critical temperature of this superconductor are high, but not so high as cuprates, okay? In the one we were working experimentally, the critical temperature is 23 Kelvin, which is high, but not so high. You can see the...
But do you see any connection between the PS and the Chalcogen height? That's the question.
Yeah, people, but that depends on your microscopic theory.
You can control the TC, right?
Yes. You can control the TC with doping, okay? And depending on the microscopic theory you are going to choose, you can explain the critical temperature with the position of the atom. But then you have to commit to a microscopic.
But the TS for the
The what? The TS.
Yes. Can you control it?
Yes. You can, but, well, what they measure is the structural transition, okay? So they measure with X-rays, suppose, okay? And that depends on doping. See, I mean, if you mean that controlling, yes, you can. Sorry, I need to come back to the... Here, see? I don't know if that's a question, but you see, this is the structural transition that depends on doping, okay? So, but then you have to believe that the nematic transition is in top of the structural transition, which is an act of faith.
Okay, I have two questions, perhaps not so, I'm not sure are related to your study actually, but
okay.
Let's see. People when applies magnetic field and measures the all resistivity in cuprates, they often say that they see a change of sign in the all resistivity. And there are works explaining this with a structural, well, with a Fermi surface reconstruction, perhaps related to some charge density way, whatever. My first question is whether vortices can contribute to this change of sign in the all resistivity, if you know if this is something has been overlooked, because people have been discussing a lot about the electronic part, and not about...
Yeah, but they measure in the...
The claim is very high field, but...
But they don't measure, I think they don't measure in the superconducting phase. They measure over the superconducting phase where there is resistivity.
I think that they go down in temperature, so at some point they should enter the superconducting phase.
We did in the I can show you later, in the first experimental work, we measured, when we know, I mean, the experimentalists I was there watching, they measure resistivity in the superconducting phase. Okay, but then you have a very, very tiny window of temperature when you have resistivity, because then it dies completely. And you can play about how that depends with the orientation of the magnetic field.
Well, we talk about
but at the sign, I don't know.
Okay, that's just a comment. I saw a recent experiment of Dragana Popovic.
Okay.
She was measuring lanthanum, and okay, that was a surprise. Besides the change of sign, the all resistivity was systematically going to zero, but really zero. And this is strange, if you want. So I don't know if this has, perhaps could have something to do with the vortex state.
I have to. There is a difference with high, because that's a high TC, no? High TCs in top of the superconducting are insulators, and these are bad metals. So I don't know whether it's the same, but we can look if there is any work, if it is an analogy.
I also have two questions, not very far from what Marcello said. These TCs for the superconducting are not very high.
No.
Right? So can you just kill TC with a magnetic field and look at the temperature? Yes. Has anybody done that, or will the magnetic field affect the
nematicity? You can calculate the critical field, and it will happen like any superconductor, where there is a critical field, after which you destroy the superconductivity.
And this nematicity is alive once you apply that magnetic field, or does it have an influence?
Well, I specifically I don't know of any experiment, but I guess there has to be some because as I told you, nematicity is almost always studied in the non-superconducting phase, where things are metal. So
yeah, but if you killed superconductivity at low temperatures, it's still metallic, right?
Yes, but people agree that there is nematicity when there is no superconductivity. What people don't know very well is if there is the nematicity in the superconducting phase. In the normal phase, people argue that, yes, nematicity plays a role.
And my other question is very naive.
Yeah.
It's a bad master student's question. But what is the difference between nematicity, charge density wave order, or stripes?
Oh, yeah. Well, there is a nice review by one of my authors that has like 300 pages. This. You should. The answer is there, but I mean, the phenomena are different because those are linked with magnetic order, and here people are not sure whether nematicity has anything to do with magnetic order. Also, the order parameter is different. So when you write the free energy, in principle, you have different terms according to the situation. But the phenomenology is not so different. There are many common stuff, but those stuff that appears in cuprates are similar, but not exactly the same. Okay, so different order parameters, and the origin is different, but are different, but not so different.
Thank you.
We have time for maybe one more question. Are there any from the students, maybe, or from? Yeah, we've time. Yeah, okay, good. We want to encourage the students to talk, right? So then we can wait 2 minutes for the coffee.
Also, hi, thank you for the talk. I study other structures, so is there any measure, because you're talking about crystals, crystal iron, iron oxide. So if you have, can you tune TC or maybe TS by controlling the substrate? Maybe grow a thin film of the iron superconductor and try to control the plane with the substrate. Like trying to make a better window to maybe measure experimentally or to tune the character, maybe make the nematic phase stronger or some influence for the substrate of this.
Yes.
Yeah, the strain or charge.
No, yes. The answer to your first question, I don't know, because I'm very far from chemistry. I can give you the reference. One of our students is working in that lab where they build these crystals, okay? And I don't know how they do it and how. I mean, for our group, they send us the crystal and say measure it, so we trust them. It's a group in Ames University, so I don't know. Then the other thing is with the strain. I mean, pulling and compressing the sample. Yes, is that what our group does? The experimental group didn't invent the method. It was invented by someone called Higgs. Not Higgs of the particle, but Higgs with C. It's written like this. They invented a very clever apparatus to take a tiny crystal and to push and to compress them. Technically, it's very difficult to do. They use a very clever technique. And then what people do is to study how the critical temperature changes with stress and things like that.
Okay, but I think if you have another material,
you have
another material. A thin film of this iron superconductor and another material below.
Yes.
You have an interface.
Mm-hmm.
Can you use the interface strain together with the break in the symmetry of the book to tune? Does it exist?
I don't know because I'm not able to produce the. We don't. I mean, we get the material, and the only thing they do is to put contacts to measure resistance, but we don't manipulate them with other interfaces. I don't know. Probably some people can do it. We can have a look. Yeah, we don't know.
Okay, then I think in view of time, we should thank Gustavo again, and we can have a coffee break.
Okay, thank you.
And we meet again for the next talk at 10:30.